Thank you for your brief introduction and inviting me to the Nelson Lab Symposium. My name is Michael Spalek. I'm responsible for research and development in the Romelag Group, and I will guide you through blow fill and seal technology, specially dedicated to large volume parenteral packaging. This is a short overview on the next 22 minutes. First, some words concerning Romelag, the company, and of course, I will introduce the principles of blow fill and seal. Number 2 is then container and material selection, followed by number 3, recent innovation in LBE packaging. And of course, I will end up with a short summary. What is Romelag? Romelag is the brand name of the group of our companies. The biggest divisions are Romelag Engineering and Romelag CMO, or more precisely, Romelag CDMO. Romelag Engineering, they do produce the machines, develop the machines, etc. Whereas the CDMOs use our machines for producing containers for the pharmaceutical and medical industry mainly. Kocher Plastic, the main machine building company, is situated in Germany with approximately 700 people working there. The smaller company, around 100 people working in Switzerland at Maro Plastic. Holopack and Maropack are the two CDMOs, same in size, situated also in Germany and in Switzerland. What about blow fill and seal? Blow fill and seal is based on the well-established and well-known extrusion blow molding principle. With that technology, billions of containers are produced annually, for example, for personal care, for food packaging, and other applications. The technology starts with polymer granulate, which are heated up and extruded and transported through that extruder screw into a molten state and then into the parison head. The parison head then forms a hollow tube, the so-called polymer parison. And now you can use that polymer parison to form containers by blowing or other shaping technologies. But for pharmaceutical packaging, you need much more. So our technology, the blow fill and seal technology, is based on that technology. We extrude the parison into a mold. Second step is blowing with sterile air into the still deformable warm container to shape the container into a bottle, for example. Next step is filling immediately after blowing, because we have a combined blowing and filling nozzle. Then immediately after that, sealing takes place with the head mold that closes and weld seals the container. And the last step is demolding. The mold opens and you can remove the container and put it into the next steps like inspection or labeling. Very importantly is to notice that the cycle time is approximately 15 seconds only. So from a rigid polymer granulate into a filled closed container, it takes just about 15 seconds. And of course, we do need sterile blowing air and sterile filtration for the formulation. Looking onto the process in more detail, that's a short video. You see here the parison head. Here we do extrude 8 parisons, 8 polymer tubes in parallel. and the mold is picking up these polymer tubes for the process, extrusion of the polymers. Mold takes the parissins into the filling and blowing position, blowing up sterile air, filling with the formulation, head mold closes, and you have the final primary container. Again, extrusion, cutting with that hot knife, transferred to the blowing filling station, blowing nozzle blows up, filling takes place, and the container is tightly closed by the sealing due to the head mold closure. Looking from above, this is a short um, layout of the system. So we typically have the separation into a dark side and a white side area. On the dark side, you have the equipment cabinet and the electrical cabinet. You have a polymer feed for the polymer granulate that feeds the extruder. The extruder melts and transports the molten polymer to the Parisson head, indicated here. Then at the A zone, you do the blowing and filling steps and the closing. Of course, we do also have sterile filters for the formulation and for the air. And from the buffer tank, we have the formulation transferred into the container by typically time pressure dosing. Mold opens and we can transfer the containers into the next steps. A machine looks like that. This is an example of a bottle pack 321 machine. Key features are we are classified as advanced aseptic processing, following the guidelines of the US and the European authorities. We do have hygienic design as well as, and that's very important, an ultra compact A zone where the critical steps do happen. Typical production capacity for a LVP container of 250 milliliters ranges from 2,000 pieces an hour, resulting into 12 million of containers produced annually, up to 8,800 pieces, resulting into more than 50 million containers per year. What about container designs, container shapes? General blow, fill, and seal can be used for very small containers, as shown here in the eye care section, where we typically have 0.2, even less, milliliter filling volume for these single dose eye drops. In the mid-range, we have the inhalation drug products and the small volume parenterals. These are in the range of typically 1 to 20 ml. And as for today, for the large volume parenterals, we typically have 50 milliliters to 100 to 1,000 milliliter filling volume. Design-wise, we cover bottle type and bag type containers. Bottle type of containers are shown here, but we can also do bag type containers, which are hanging here. Most of our customers currently prefer the bottle type of containers with a freestanding containers being easy to manipulate, to label, and to administer in the hospital. What about materials? Blow, fill, and seal, like ampule production, we do have single drug contact materials, and we do prefer the medical grade polyolefins. These polyolefins are typically LDPE or polypropylene, delivered by companies like Borealis or LyondellBasell. You might have listened to the presentation of Anja Gottschalk from Borealis. The most important selection criteria between LDPE and PP certainly are the requirements for terminal sterilization. This is typically done by autoclaving. And if you have a product that needs a high autoclaving temperature as recommended by the authorities, then polypropylene is a good choice. Whereas if you have a thermal not that stable formulation, LDPE would also do a good job. We are in a Nelson Lab symposium. That's why you have to deal with extractables as well. So we did so. Together we worked out extractable dossiers for some of our most used polyethylenes and polypropylenes, former times with Toxicon, now with Nelson Labs. And here is a summary from Pete Christians from our conference, PDA conference 2016. One line summary for aqueous drug products, the extractable results show a low risk of leaching of components to a relevant level. That means that extractables and thereby leachables do not play a high risky role when using blow fill and seal packaging. For dedicated requirements like oxygen barrier or low adsorption formulations, we can use co-extrusion and or the cyclic polyolefins COC and COP. Here is the principle of multi-layer containers and co-extrusion. You do not produce just one parison with one material, but just one parison with various materials, a multi-layer system. And in the multi-layer system, you might integrate a barrier layer. And that barrier layer, for example, would block oxygen quite efficiently and also odors or other substances you do not want to enter the container. For oxygen barrier, typically EVOH is a good choice of material. If you deal with adsorption and uh, adsorption topics, then you would probably use the cyclic polyolefins that give you a very low adsorption on the inner surface of such a container. Transferring that into machine building, that means you need more extruders and a dedicated parison head where you feed in the respective materials as needed. In that case, COC, COP on the inner layer would give you low sorption and good barrier against adsorption into the system. What about efficient material selection? Therefore, we developed a so-called BFS test kit that allows easy pre-testing and easy compatibility testing with most of our standard blow fill and seal materials. Therefore, we did produce empty closed containers. Normally, we don't do empty containers, but for that topic, yes. Empty closed containers produced following GMP regulations inside sterile. These containers can then be used in your lab quite easily for doing compatibility testing, for example. Test kit handling is straightforward. You open the container. This is the 10 ml test kit container. You cut it open. You fill it with a syringe or a birette. You warm it up with a heat gun, just the top of it, and you close with a gripper, and you thereby nicely seal the container. Now you can transfer the container to the stability chamber or do the compatibility testing. You can close and reopen the container several times, extract some solution, etc., etc. So that's quite easy, especially if you are very short in active substance in formulation. This gives you a very straightforward testing method and allows good material selection. Let's look into our recent innovation in LVP. These are the easy empty bottles. Looking into the market, as outlined, we do have LDPE bottles that are all fine, safety, particulate matter, container size, etc. All is fine. However, sterilization is to be improved. That's why PB bottles are on the market, benefiting from the higher thermal resistance of the polypropylene. Here, sterilization is not an issue anymore. However, you need to increase the container size to have an administration procedure, an application without venting the container. That's fine for the LTPE bottle because it's soft. It's not so good for the PP bottle because this is much more rigid. But from the microbiology point of view, you want to avoid having a vented container. That's why we put up the development task having a high performance self-collapsing container. So the new bottle should fulfill all these requirements quite nicely. How did we approach that? Thinking first into the categories of an Ishikawa analysis gives you the main parameters you can play with. In our case, our target is having a safe, efficient infusion administration and having a non-vented system. We can play with material, BFS process, and container design. We cannot influence the medical requirements dramatically. So material-wise, the most important parameter certainly is the Young's modulus. For the BFS process, the wall thickness and the wall thickness distribution is important. Whereas for container design, the shape and the headspace to fill ratio is important. So playing around with these parameters was the goal to get into a good solution. We started with just looking. That often helps in development. So we have analyzed various standard bottle designs and looked what happens if you completely empty them just by pressing them or sucking with under pressure to really make them collapse. And if you now highlight these features of a completely collapsed standard container, you see what happens and what is needed to have a good collapsing behavior. We now took these criteria, hinges, folding triangle, folding edges, into our CAD design, our mold design. Next step. Then we would need to produce the molds and do the tests. However, there are so many minor possibilities to go into all these details. We then said, okay, we do not want to build 20 molds. We want to use simulation as a tool in order to avoid costly and time consuming development efforts. So we went into a simulation system, looking into an FEM simulation shown here. The filled container is continuously emptied during administration. So this is discharge time, beginning and end. And at the end, you see a collapsed container. And from this simulation, we could learn about the detailed specifics of the container needed, as well as what has been foreseeable, that we want to use a material, a polypropylene preferably, with a low Young's modulus in order to make collapsing as easy as possible. We then built the mold and did the tests. You see the results here. On the left-hand side, this is our easy empty bottle, 100 ml, made from polypropylene. On the right-hand side, it's a bottle from the market, existing bottle from the market. And now we can compare. Starting the video, we are emptying the container now into that cylinder. This is a fast motion, otherwise we would need 18 minutes more until the easy empty container is empty. You see at the beginning they are quite similar, but now at the end of administration, the easy empty container is very superior, empties completely after 18 minutes, whereas it takes much longer for the standard polypropylene bottle from the market. This was the proof that simulation and reality nicely fit together, not perfectly, but quite nicely. Let me summarize. Blow fill and seal technology in large volume parenteral packaging. In seconds, blow fill and seal produces filled containers, tightly closed, with machines that are very compact in size. Material-wise, we do prefer the polyolefins, and this is then the single drug contact material. Extractables and thereby leachables are not of a high concern. For special applications, we can use co-extrusion and or cyclic polyolefins, COCs, COPs, for example, for requirements on low adsorption to the inner surface. With our BFS test kit, we can have an easy pre-test for material selection, for compatibility testing, etc. And for our new easy empty bottle, the administration behavior nicely compares to established products on the market. My last slide gives you some literature for further reading, and I'm available for further questions. Thank you very much.